Hello everyone. Today we are going to start with the second and third case of Frobenius method. Before going on to that, we are going to learn the method to find the second linearly independent solution if one solution is known. That means suppose y1 be the solution of equation y double dash plus pxy dash plus qxy is equal to 0. Then the second solution is given by y2 is equal to u into y1, where u is nothing but it is integration of 1 upon y1 square into e raised to integration minus p dx. Now see, we are going to use this if one solution is known. Starting with the example of Frobenius method, first we are starting with example x into x minus 1 y double dash plus 3x minus 1 into y dash plus y is equal to 0. Near x is equal to 0. Now see, first we are going to write this equation in standard form, and that will give you y double dash plus 3x minus 1 upon x into x minus 1 y dash plus 1 upon x into x minus 1 y is equal to 0. Comparing this with our standard equation y double dash plus pxy dash plus qxy is equal to 0, we have px is equal to 3x minus 1 upon x into x minus 1 and qx is equal to 1 upon x into x minus 1. Here px and qx both are not analytic at x is equal to 0, correct? So we have both non-analytic function, and therefore px and qx are not analytic. That means x is equal to 0 is a singular point. Therefore we are going to check the regularity of it. For that we are starting with x minus x0 into px and x minus x0 whole square into qx. If you are going to find them, and then at x equal to 0 both has a finite value and therefore they both are analytic. So x is equal to 0 is a regular singular point. Now we are starting with our standard assumption y is equal to x raised to r sigma an x raised to n, whereas 0 is not equal to 0, be a trial solution of equation 1, multiplying x raised to r inside x raised to n, and that will give y is equal to sigma n running from 0 to infinity a n x raised to n plus r. Y dash will be n plus r a n x raised to n plus r minus 1. Double dash will be a n plus 1 n plus 2 n plus r n plus r minus 1 a n x raised to n plus r minus 2. Putting these values in equation 1, and that will give you x square minus x into y double dash, that means sigma n plus r minus 1 a n x raised to n plus r minus 2, 3x minus 1 into sigma n plus r a n x raised to n plus r minus 1 plus sigma a n into x raised to n plus r is equal to 0. Now what we are going to do, we are going to separate out the terms x square into whole term, x into whole term, 3x into whole term and 1 into whole term. That means totally we have 1, 2, 3, 4 and 5 terms. So what we are going to do, we are going to write it in simple form. So sigma n running from 0 to infinity n plus r minus 1 a n x raised to n plus r minus sigma n running from 0 to infinity n plus r minus 1 a n x raised to n plus r minus 1. Same manner 3x will be multiplied with y double dash will give you 3 of n plus r a n x raised to n plus r, and 1 into y dash, that will be sigma n running from 0 to infinity n plus r a n x raised to n plus r minus 1. Y remains as it is. Now what we are going to do is, we are going to combine the terms with x raised to n plus r. So this one is, second one is this, third one is this. So a n x raised to n is common out, and we will have n plus r into n plus r minus 1 plus 3 into n plus r plus 1 into an into x raised to n plus r. And the two terms with x raised to n plus r minus 1, this one and this one, we are going to common out an x raised to n plus r minus 1. That will give you second term minus of sigma n plus r minus 1 plus 1 into n plus r an of x raised to n plus r minus 1. Now simplifying, here separate two terms, n plus r into n plus r, that will be n plus r whole square, minus 1 into n plus r plus 3 into n plus r plus 1, and here minus plus 1 cancel out, so you will have n plus r. Here see, if we are simplifying, then this two term will be reducing in a form of 2 of n plus r. So this is x square plus 2x plus 1 form. So it is a n plus r plus 1 the whole square into an x raised to, and this term will be n plus r the whole square. Now see, this power is n plus r, this power is n plus r minus 1. So we are going to reduce all powers in the lowest degree form. So the lowest degree will be x raised to n plus r minus 1. So lowest degree, so here we are going to replace n by n minus 1, and that will give you sigma n running from 1 to infinity n plus r whole square a of n minus 1 x raised to n plus r minus 1, minus this term remains as it is. Now see, this index is starting from 1, this index is starting from 0. So the term of 0 we are going to write it separately. That means only we are going to put n is equal to 0 here. That will give you r square minus a0 into x raised to r minus 1, and the remaining term remains as it is. So remaining sigma we are going to write it as it is from n running from 1 to infinity. Now see, these two sigma have a same index from 1 to infinity, and power is same. So we are going to common out the power x raised to n plus r minus 1. So minus r square a0 x raised to r minus 1 plus sigma common out, n plus r whole square common out, x raised to n minus r, n plus r minus 1 common out. So you will have n minus 1 minus a. Now compare the coefficients with 0. Comparing coefficients with 0, that will give us r square into a0 will be 0, but a0 is not 0, that will give r is equal to 0, 0. Now r is 0, that means r1 and r2 both are 0. So we have a case of repeating. So comparing both sides, second coefficient of x raised to n plus r minus 1. So from that one you have an minus 1 minus an into n plus r whole square is equal to 0. Now see, this term is not going to be 0 for all values of n. That means this term must be 0, and that will give you an minus 1 minus an is equal to 0, and that will give you an is equal to a of n minus 1. Now n is equal to 1, then you will have a1 is equal to a0, n is 2, then a2 is equal to a1, but a1 is a0, that will give you a2 is equal to a0. Same manner, n is equal to 3, then a3 is equal to a2 is equal to a0. Same manner, for n is equal to 4, you will have a4 is equal to a0. And if you are going to put all these values in your series, then your series equation number 2 will reducing in a form of x raised to r into a0 plus a0x plus a0x square plus a0x cube and so on. a0 will be common out, that will give you a0x raised to r into 1 plus x square plus x cube plus so on, so on, so on. Now this is nothing but it is the series of 1 upon 1 minus x. Okay, so y will be reducing in the form of a0x raised to r into upon 1 minus x. Now what we are going to do is, we are going to substitute value. So y1 will be obtained by putting r is equal to 0. So put r is equal to 0, that will give a0 into 1 plus x square plus x cube and so on. Or if you are aware of the series, then it will be a0 into 1 upon 1 minus x. Same manner for y2, what you have to do is, you have to differentiate this term with respect to r. So if you are partially differentiating with respect to r, then in that case r is a variable, x is constant. X is constant, so constant raised to something as a derivative. So So x raised to r has a derivative x raised to r into log x. A raised to x has a derivative a raised to x into log a. So here you are going to put r is equal to 0, and that will give y2 is equal to a0 log x upon 1 minus x. So your general solution will be of the form c1y1 plus c2y2, that is c1 upon 1 minus x plus c2 into log x upon 1 minus x. I already told you that a0 and a0 will be going with c1 and c2, that will give you new constant. So now we are going to ignore the constant a0 in general solution. Same in the third case, we are going to take it for the equation x square minus xy double dash minus x into y dash plus y is equal to 0. So again we are writing it in the standard form, y double dash plus x upon x square minus xy dash plus x square minus 1 upon x square minus xy. From this one we have px is equal to minus x upon x square minus x, qx is equal to 1 upon x square minus x. So px will be minus 1 upon x minus 1. Now see here, px is finite but qx is infinite at 0. So qx is not analytic at 0, and that's why x equal to 0 is a singular point. Again we are going to check the regularity of it. So x minus x0 into px, x minus x0 whole square into qx, both has a finite value at a 0, and that's why x equal to 0 is a regular singular point. So as per our assumption, assume that y is equal to this x raised to r sigma a n x raised to n, where a0 is not 0, be a trial solution. From that we are going to find y dash and y double dash, and we are going to put all values in equation 1. Now if you are going to put in equation 1, then sigma x square minus x into sigma n plus r minus 1 a n x raised to n plus r minus 2 minus x into sigma n plus r a n x raised to n plus r minus 1, and the last one will be sigma a n x raised to n plus r is equal to 0. Now here we have a two terms, x square into y double dash, x into y double dash. This x will be going with a multiplication of a power of x. So we have totally 4 terms. First will be sigma n plus r minus 1 a n x raised to n plus r. Second will be n plus r minus 1 a x raised to n plus r minus 1. Third will be x raised to n plus r a n x raised to n plus r. Fourth will be a n into x raised to n plus r is equal to 0. Now what we have done is we are going to combine the terms of x raised to n plus r, n plus r, n plus r. So these 3 terms will be going to be combined. So a n x raised to n plus r common out, and you will have n plus r minus 1 minus of n plus r plus 1 into a n x raised to n plus r minus this term remains as it is. Now what we are going to do is we are going to combine the second, simplifying this term, that will minus common out, that will give n plus r minus 1, and from this 2 if you are going to common out n plus r minus 1, then here you have n plus r, here you have minus 1. So n plus r minus 1 into n plus r minus 1, that will be a n plus r minus 1 the whole square. Second term remains as it is. Now you have to change the index, because see here you have power x raised to n plus r minus 1, here you have x raised to n plus r, but the lowest degree is x raised to n plus r minus 1. So that's why what we are going to do, we are going to replace n by n minus 1. So you will have n is running from 1 to infinity, n plus r minus 2 whole square, a of n minus 1 x raised to n plus r minus 1, minus sigma n running from 0 to infinity, n plus r minus 1 a n x raised to n plus r minus 1. Now since both powers are same, now you have to check out the index. This index is starting from 1, this index is starting from 0. So for in second one we are going to substitute, in this one we are going to substitute n is equal to 0, that will give you r into r minus 1 a0. So r into r minus 1 into a0 x raised to, and then sigma remains as it is from n is equal to 1. So this term remains as it is, and from this 2 we are going to common out sigma and the power of x. So x raised to n plus r minus 1 common out, and here you will have n plus r minus 2 whole square a n minus 1 minus n plus r into n plus r minus 1 a n. Now compare the coefficients. So x raised to r minus 1, so this coefficient is equal to 0, that will give r is equal to 0 and r is equal to 1. So smaller one is r1, greater one is r2, and r2 minus r1, so r0 is r1 and r1 is r2. So r2 minus r1 is 1, and that will be integer. Now this is our case 3. For case 3, what we have to do, we have to simplify whether it is a logarithm case or non-logarithm case. That means one of the coefficient is infinite or it is becoming indeterminate. So for that we are going further. Now the second term, this x raised to n plus r minus 1, and the coefficient is n plus r minus 2 whole square a of n minus 1 minus n plus r minus 1 a n is equal to 0. From this one we have a n is equal to n plus r minus 2 whole square divided by n plus r minus 1 a of n minus 1. Put n is equal to 1, that will give you a1 is equal to r minus 1 whole square upon r plus 1, r is equal to 0. Same manner, put n is equal to 2, that will give you r square upon r plus 2, r plus 1 into a1. But a1 has a value this, so substitute this value here and simplify, that will give you a2 is equal to r into r minus 1 whole square upon r plus 2, r plus 1 whole square. Now putting these values in equation, that will give you y is equal to x raised to r a0 plus r minus 1 whole square upon r plus 1 upon r a0x plus r into r minus 1 whole square upon r plus 2 r plus 1 whole square a0 x square, and so on. Now if you are going to put r is equal to 0, for the smaller value, this coefficient, second coefficient, becomes infinite, the coefficient of x. So in that case, this is the case of logarithm. Here you have to replace a0 by b0 into r minus r1, but r1 is 0, so it will be b0 into r. So a0 will be replaced by b0 into r, b0 into r, b0 into r. So here r will be cancelled out, and your equation is reducing in this form. Y is equal to x raised to r b0r plus r minus 1 whole square upon r plus 1 b0x plus r square upon r square into r minus 1 whole square upon r plus 2 r plus 1 whole square b0x square, and so on. Again put r is equal to 0. Now if you are going to put r is equal to 0, then the first term and the third, all the terms after the third term and onwards are going to be 0, and that's why that answer will be in the form of y1 is equal to b0x. So for y2, what we are going to do, we are going to ignore the constant, that's why we are going to put b0 is equal to 1, and that will give you y2 is equal to u into y1. So putting this value in u into y1, where u is equal to, again the method of reduction of order, u is equal to 1 upon y1 square e raised to integration minus p dx. Putting the value of p and integrating, that will give you u is equal to log x plus 1 upon x. So y2 will be 1 log x plus 1 upon x into x, and that will give you y2 is equal to x log x plus 1. And that's why you will have general solution is c1y1 plus c2y2, where c1x plus c2 into x log x plus 1. Or you can, instead of this method, you can use the second method, that is a derivative method, which we have used for repeating root. That means one solution you have obtained, y1 is already here. For y2 you have to differentiate this term with respect to r, and then again put r is equal to 0. So this is the case of logarithm 1, and for that you have C1. Here the last one is a case of non-logarithm 1, and see, check out this by yourself. See, first we have find px, qx, x equal to 0 is a singular point. Then we have check it is a regular singular. Then our standard assumption. Then we are going to put all values in our equation. From that we are going to compare the coefficients. Up to that it is okay. See, here you have n is running from 0, and here it is running from 2. So here you have to separate two terms for n is equal to 0 and n is equal to 1, and then sigma remains from 2 to infinity, and this term remains as it is here. So from the first one you will have r is equal to 0 and r is equal to 1 minus 1, sorry. So r is equal to 0 is smaller, greater 1, so it is r2, and minus 1 is r1. So r2 minus r1 will be 1, and that is the case 3, which is a case of integer. Now here from the second term you are not going to find the values of r. You are going to find the values of r from only the lowest degree terms. So from the second one, what we are going to use, whatever the values of r we have already obtained. The values of r, so smaller value is minus 1, and if you are going to put minus 1 here, then you cannot find the value of a1. So a1 is going to be indeterminate. Now this is indeterminate, so the general solution is simply obtained by putting r is equal to r1. So first for that we are going to compare the coefficient, put all values, find the values of an, that will give an is equal to this. So putting n is equal to 2, that will give a2 is equal to minus a0 upon r plus 3, r plus 2. N is equal to 3, then a3 will be minus a1 upon. Now see, here you cannot find a1 because a1 is indeterminate, so a1 remains a1. And now you have two coefficients, a0 and a1. So your answer is now onwards containing a0 and a1 both. So if you are going to put all values here in y, then your equation is of this form, and in that you are going to put r is equal to minus 1. So if you are going to put r is equal to minus 1, then it will be of the form x raised to minus 1 a0 plus a1x minus a0 by 2 into 1 x square minus a1 upon 3 into 2 x cube plus a0 by 4, 3, 2, 1 x raised to 4, a1 upon 5 into 4 into 3 into 2 x raised to 5, and so on. So separating the terms of a0 and separating the terms of a1, you will have 1 minus x square by 2 factorial x raised to 4 by 4 factorial, and so on. Same manner here you have x minus x cube by 3 factorial x raised to 5 by 5 factorial, and so on, and that will give the general solution. Okay.